Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at your Bellwork. So we've seen the graph of a quadratic equation, right, is our parabola. And it could be a right side up or upside down bowl shape. In this particular equation, y equals negative x squared plus 6x minus 4. What's the general shape or direction of this? Kinsey? Absolutely. We've got an upside down parabola. So in general, what does this look like? Without plotted points or a table of values or a graphing calculator, we could just say this is an upside down parabola. What was it about the equation that indicated this would be an upside down parabola, right? What's an indication this would be an upside down parabola before we ever looked at a graph, but just by looking at the equation? Mark? Absolutely. This negative multiplier on my quadratic term, the x squared, means that we're going to have an upside down parabola, right? An upside down parabola. Nice. So let's go ahead and solve this equation and find the solutions to that. And we're going to go ahead and use the quadratic formula to practice. So last class, we generated the quadratic formula as a formula that will always work when solving quadratic equations. For that reason, it's very powerful. So we could try, factoring this or completing the square, or lots of different ways that we could try to solve this. We're going to practice with quadratic formula. So be ready, because I'm going to call on you for the values I'm going to use for A, B, and C. But first, I'm going to go ahead and remind us about the quadratic formula. We know that x is given by the opposite of b over twice the value of a plus or minus the square root of b squared minus 4 times a times c closed radical all over 2a. If I memorize that quadratic formula, right, then all I have to do is plug in my values of a, b, and c for my quadratic equation set equal to 0 in standard form, and it'll tell me what the answers are. It'll spit out what the solutions are. And so that's why it's so powerful, and it always works. What am I going to use for a here? What am I going to use for a? Nathan? -1, thank you. So I'll use -1 for a. What will I use for b? Carson? 6, thank you. Or I'm going to use the value of c. Aaron?
-4.
Thank you. Let's go ahead and now evaluate my quadratic formula. X equals, but everywhere I see a b, I'm now going to put 6. Everywhere I see an a, I'm going to put -1, and so on and so forth. So let's go ahead and do that and see if we got the same thing. Awesome. So everywhere I see an a, I'm going to put -1, -1, -1. Everywhere I see a b, I'm going to put 6. And everywhere we see a c, we're going to put -4. I just messed with the colors, didn't I? Well, we're going to have to stick with it. We're going to have to stay strong. We're going to have to fight it. Ooh, but I want PDF to go. It's so hard. It's going to have to change it. I can't handle that. It's okay. I know some of you in here were like, oh gosh, I don't know if we can export that in PDF anymore. All right, so let's go ahead and evaluate and see what we get. We're working out negative, right? Opposite of 6 is going to be -6 over 2 times -1 is -2 plus or minus the square root of. And now we're going to hop inside there. Remember, b squared is always positive. So even if you had a negative value of b, when you do b squared in the quadratic formula, the result will always be positive. -4 times a times c is going to be -16. Right? Is that right? -16, because negative times negative times negative overall is a negative. All over twice the value of a is -2. So it looks like we've got some work to do this time. All right, I'll do one more step on this side, and then I'll scooch over. So -6 over -2 is +3. There's my axis of symmetry, right? There's my x-coordinate of the vertex. There's my invisible vertical line that cuts the parabola into 2 equal left-right halves, plus or minus. Now let's figure out the distance that we could walk on either side, to the right or to the left, along the x-axis, and get to my x-intercept. So it looks like 36 minus 16 is that 20? 36 minus 16 is 20, so I'm getting root 20 all over -2. And I know that that root 20 will simplify to 5 times 4 inside. So 5 times 4 inside is going to become 2 outside, and then root 5 still, and then negative 2. Means that I could do one rewrite. This negative sign here multiplied by the plus or minus would result in a minus or plus, which is still 1 plus and 1 minus. And so however you want to write it, I'm going to go ahead and reduce this as 3 plus or minus root 5. I'm going to do 3 plus or minus root 5. So that's 2 different solutions. One's given by 3 plus root 5, right? And one's given by 3 minus root 5. What questions do you have about generating those with the quadratic formula? So raise your hand if you got that. Did anybody get all the way to the root? You could have root 20 still over, right, over 2. So, okay, good, good. So let's go ahead and now see how we can verify that using the built-in capabilities of our calculator. So now, what do our solutions represent graphically, right? What do those represent graphically? When we go and look at the picture, what do we expect to see? Ian?
Those are the x-intercepts.
Yeah, the x-intercepts. And so my solution values are the x-coordinates of the x-intercepts. And so what I'm going to do here is I'm going to go ahead and, as we've done in the past, I think I'm going to actually write x equals 3 plus root 5. Right? That's one x-coordinate of an x-intercept. My other one I'm going to write x equals 3 minus root 5. We'll box those. That's awesome. So those x values are the x-intercepts of my graph. They're the x-intercepts of my graph. State the axis of symmetry. The axis of symmetry, algebraically we determine, is the first part of that quadratic formula. It's the opposite of b over 2a. So if we look back at our work, right, we find the opposite of b over 2a was that first term that simplifies before the plus or minus. What's the axis of symmetry going to be for this graph? Jacob? Is it negative 3? Opposite of b over 2. I could have messed up. Opposite of b, negative 6 over b. No, so it looks like positive 3? Positive 3? Okay. So it looks like my axis of symmetry, remember, is a vertical line. And so I'm going to go ahead and state that as an x equals equation. X equals positive 3. And now I think we're ready to check graphically. So we're going to use our graphing calculator and the trace feature to verify each of our answers above. So what we're going to do is enter our original equation, y equals, in our y equals menu. So everybody, let's go ahead, if you haven't done so already, let's go ahead and enter our original equation in our y equals menu. Y equals negative x squared. Thank you for doing this. We always want to check with our trace feature, so this is an important skill. Minus 4. So negative x squared plus 6x minus 4. We're going to go ahead and zoom 6 to get a standard viewing window and see if we can see our graph. And it looks like, yep, Kenzie was right. We have an upside down parabola. And we don't know what my zeros are. We could calculate them and get a decimal approximation, except that we do know what our zeros are because we've already solved my equation set equal to 0, and we generated 2 solutions. X equals 3 plus root 5, and x equals 3 minus root 5. So what we're going to do right now is enter that as a x value in the trace menu, enter and see if it jumps on the graph. So we don't know what that is as a decimal, right? We're going to go ahead and enter that exactly and see if it jumps on the zeros. And so this is a way where we can make that connection, right, between the x-intercept and our solution values. So let's go ahead and enter trace. And I'm going to put my x value of concern. One x-intercept I thought was 3 plus root 5. So I'm going to do 3 plus root 5. I'm going to enter that in my calculator. And I'm going to press enter. And then voila! It jumps on the graph at a decimal that's about 5.236 and pairs it with the corresponding y value of 0. That's an indication that I have correctly found the x-intercept of the graph. What other x value do we want to check? Right? What other x value do we want to check? Andrew?
It would be the 3 minus the square root of 5.
Cool. So we can trace and then enter the x value 3 minus the square root of 5. Right? And then enter. and it's jumped on the graph and paired it with the y value 0. So I know I'm correct. That's pretty awesome. So we've got our solution values, and I'm feeling pretty good about that. And so the only one I didn't take was the 3 plus root 5. Oh boy. Oh jeepers. I'm going to grab that. Okay. Awesome. What questions do you guys have about that trace feature? So that was when we have an x value in mind, right? We can pick trace and then enter my x value, enter, and it'll jump on the graph and pair with the corresponding output. Versus, what was that other one if we wanted to find? If we didn't know the solutions, what if we wanted to find that x-intercept, right? What was the command for that if we wanted to find that x-intercept? What do we do then? Hannah? Yeah, it was the second trace of the calc, and then it was the. Do you remember which? It was. It didn't say x-intercept, but zero. Absolutely. So if we didn't know what the value was, we could do this. When we did this on our calculator, and it tells me the x-intercept coordinates, it's going to give me a decimal though. The only way to get that exact answer, 3 plus root 5 or 3 minus root 5, was to either use the quadratic formula or completing the square. So we can't factor that, right? If we want to get the exact answer, we have to do it algebraically by either using quadratic formula as we did in today's Bellwork or completing the square. That's pretty awesome. What questions do you guys have about your Bellwork? That's a great Bellwork and a setup for our discussion today. Right? We're going to go ahead and graph parabolas today. We're going to find the vertex by hand. We're going to make a picture of our parabola, and we're going to see what the discriminant tells us about the number and type of our solutions to the quadratic equation. So a big day today, an exciting day today. But first, let's go ahead and check our assignment. I'm going to go ahead and pause the recording while we do our homework check. Today we're going to use the discriminant, which is actually part of your quadratic formula. It's hiding inside the quadratic formula, and it's going to tell us about the number and the type of solutions a given quadratic equation has. We'll take that and make a connection then between the graph of the parabola, much like we did in today's Bellwork where we looked at the graph and made a connection between our solutions. So too will we do that today during our activity 610. So I'm excited about that. We're also going to be working in our cooperative learning groups together as we work through this activity. And so we'll be moving the desks to form small islands where we work together as a team, and we're going to go ahead and see how the discriminant then influences the number and type of solutions. And so I'm excited about that. First, though, we're going to go ahead and go through and complete one together. In each case, you're going to be finding the vertex algebraically first. That is, without our graphing calculator, right? I mean, you can use the calculating on the home screen, but we're going to figure out how to find the vertex by hand algebraically. And then we're going to answer various questions about the graph, its solutions, and x-intercepts, if there are any. So that's what we're going to do. We're going to do A together, and then you'll have an opportunity to earn up to 3 stamps in your cooperative learning groups. And so at the end of each question, B8, C8, and D8, right, is going to be stamps. When you completed that and you guys all agree, then you're going to raise your hand, and I'm going to come over and I'm going to check on the group as a whole, right? Make sure you guys all agree, and then I'll issue stamps to your entire group at one time. It's important that you're working together, right? That it's not one person doing the work and other people copying, or that 2 people are working ahead and the other people are kind of visiting or falling behind, right? You all are working together to make sure that everybody understands, and that's why we're working together. I wholeheartedly believe that by talking about the mathematical concepts, not only will you understand it better, but you'll also remember it longer. And so there's multiple gains that come from working together as a team and as a group as we go through these activities together. So I'm excited about that. This is a good one. We're going to do the first one together. So everybody go ahead and just turn the page. We included it in our note sheet today, so there's not a separate handout. It's all in there. And we're going to do letter A together. So this will be kind of like a model, a template for you as you move into your groups and you continue working together. So for letter A, right, we're going to go ahead and find the vertex algebraically. The first thing we need to do is find the x-coordinate of the vertex, and that's given by opposite of b over twice the value of a. So as we look at this quadratic equation, we need to pick out the values of a, b, and c. Be ready to share with the class when I call on you. So we're in standard form, everything on one side, standard form. What would I use for the value of a in this case? Joe? 2, thank you. What do I use for B? What do I use for B? Megan? Thank you. We'll use 16 for B. And what we'll use for C? Samantha? 24. Thank you. Now we'll go ahead and evaluate. X equals opposite of B over 2A gives me the x coordinate of the vertex and the axis of symmetry. So let's go ahead and evaluate that right now. I know that x is given by the opposite of B over twice the value of A. So the opposite of B over twice the value of A. And the value of B was 16. And the value of A was 2. Make sure I have my colors matching. Oh, goodness. And it looks to me like opposite of 16 over 2 times 2 is negative 16 fourths. And negative 16 fourths is going to reduce to negative 4. So right now, I would expect my x coordinate of the vertex to be negative 4. My axis of symmetry is going to be negative 4. So it looks like my parabola has been shifted to the left 4 units, right? I'm going to make my picture, and it's going to be over here. Now, how do I find the y coordinate of the vertex? This is what you're going to have to do with your group, each problem, B, C, and D. Easy. Once I know the x coordinate of the vertex, I'll simply plug it into my original equation, y equals my function rule, and evaluate, right, to generate the corresponding y coordinate, and then write that as a point x comma y. So I'll go to my original function, y equals, and I'll evaluate it at my x coordinate of negative 4 in this case. So that's 2x squared plus 16x plus 24, except for where I see an x, I'm not going to put x, I'm going to put negative 4. So let's do that. I'll go ahead and evaluate, and I'm getting negative 4 squared is 16 times 2 is 32, minus 64, negative 32 plus 24 is negative 8. I guess I'm getting negative 8. Did I do that right in my head? Negative 8? Awesome! So I'm getting negative 8, which means my vertex as a point x comma y would be negative 4 comma negative 8. Everybody, let's go ahead and record that. So negative 4 comma negative 8. All right. So now we're going to go ahead and graph this equation by hand using our knowledge of the steepness factor, A, right? When we did our unit 1, we did our graphical transformations. Our steepness factor, that A times x squared, is going to make it A times as steep as my parent. Negative would make it upside down. We'll use that to do it by hand, and then we'll check with our graphing calculators to make sure we're doing a good job. So everybody, let's go ahead and bless you, and plot your vertex point. So here we go. Negative 4 comma negative 8. And now we're going to go ahead and use our knowledge of the steepness factor, that A value is 2, to go ahead and get integer points by counting out from my vertex. My normal parabola, y equals 1x squared, right, goes out 1 and up 1 squared, out 1 and up 1. It goes out 2 from the vertex and up 2 squared, up 4, so out 2, up 4. My normal parabola goes out 3 and up 3 squared. That's out 3 and up 9 for my vertex in both directions to get integer points. Remember 0, 0, 1, 1, 2, 4, 3, 9, because I'm evaluating y equals x squared. This parabola is going to be twice as steep. And so while my A value is still positive, it's still going to be right side up. It's going to be twice as tall. Every single y coordinate in relation to that vertex is going to be twice the distance that it normally is. And so how will we do that without a calculator? Well, we can do that simply by doubling all of my vertical heights. And so normally we go out 1 up 1. This one's going to go out 1 and up 2 times 1. We'll go back to the vertex. Out 1 up 2 times 1. So it's twice the steepness. My parabola, my parent function y equals x squared, goes from 0, 0, and it goes out 2 and up 2 squared is 4. So out 2 and up 4. This one is going to double that. So instead of going from your vertex, back to your vertex, guys, instead of going out 2 and up 4, this one's going to go out 2 and up 8 to get another integer point. Out to the other direction and up 8. So notice how my parabola is going to be twice as tall, twice as steep. My normal parabola goes out 3 and up 3 squared is 9 from the vertex. This one's going to go out 3 and up how many? How many is this going to go out? Caroline?
18.
18, exactly. Good. So out 3 and up 18. Can I fit that on here? I think I can just fit it. 8 and 10. I think we just get it, you guys. You see that? We just have enough to get a third integer point on either side. Yeah. How in the world are we getting those points? We're comparing it back to my parent function, 0, 0, 1, 1, 2, 4, 3, 9. I'm squaring my x values to get the corresponding y coordinates. Here I'm doubling those. I'm doubling those vertical changes. All right, let's go ahead and sketch a graph then. Carefully remember, a parabola is smooth. It's a bowl shape. It should be rounded, not sharp. No corners or kinks. It should be nice and smooth, even though this one's steep. Everybody have your parabola? It's pretty sweet. Good job. All right, so what do? We can now check it out. I'm going to do the same window, so I'll clear out my existing one, make sure my plots are off, and I'll go ahead and check with my grapher 2x squared. Notice how we did that by hand first, and now we're going to check with the grapher. 2x squared plus 16x plus 24. And if I zoom 6, I'll get my standard viewing window, which was negative 10 to 10 to match that. How did we do? Pretty darn well. And it's even a blue line style. Ah, very nice. I mean, not that I pay attention to those little things. Anyhow, I mean, because I suppose I kind of. All right, let's go ahead and take the original equation and set it equal to 0. So we're going to set it equal to 0 and solve using the quadratic formula. So what was my original equation? Our original equation was 2x squared plus 16x plus 24, and we're going to set that equal to 0 so we can choose our values of a, b, and c and solve using the quadratic formula. So be ready. I'm going to call on you to share with us the values of a, b, and c. Wait a minute, didn't we already do that? Did we already do that? Yeah, we've got 2, 16, and 24, right? 2, 16, and 24, so we already have those values. Good, good. And I wish I had done that. Oh, but there's hope. So I better just go like this. All right, so here we go. X equals opposite of b over twice the value of a. Plus or minus square root of b squared minus 4 times a times c. Close radical all over twice the value of a. And here we go. A is 2. B is 16. And C is 24. All right, we might need a calculator as we go to evaluate this, but I'm going to try. So here we go. Opposite of 16 over 2 times 2 is negative 16 fourths. That's negative 4. Jump inside. 16 minus 4 times 2, that's 8. Let me go to your answer. 48, 4, 200 less 6, 192. 192. Awesome. So this is 256 minus 192. And what's 256 minus 192? Is it 64? Yeah! Math's cool. Good. I think this is going to work out. I'm not saying because we could subtract that. I'm saying because I noticed that I get a perfect square inside of a square root, and that's going to make this work out very nicely. So we've got negative 4 plus or minus 8 fourths. We're so close, you guys. Which means x equals negative 4 plus 2. And x equals negative 4 minus 2, which means x equals negative 2 and x equals negative 6. Let's look at the graph. X equals negative 2 and x equals negative 6. Yes! That's exactly what we expected to see. Good news. So we'll state the number of x-intercepts on the graph. We see two x-intercepts on the graph, and that's TWO. So I'm going to write out the word so we're not confused. We'll state the x-intercepts. Well, those would be points, x comma y. So -2, 0, and -6, 0. We'll state the y-intercept. Well, graphically, I may or may not be able to see this. It looks to me like I can't see the y-intercept graphically on this window. Does that mean there isn't one? I mean, that looks pretty steep right there. Oh no, we can get that from our equation. Recall my y-intercept is always the value of my constant when in standard form. So 0, c is my y-intercept. In this case, 0, 24. So 0, 24 is my y-intercept. Very nice. That's good. And lastly, we're going to investigate the discriminant. So the discriminant is that quantity b squared minus 4ac. It's the quantity that's inside the radical. The discriminant does not have a radical in it. The b squared minus 4ac, that number, right, the quantity that's inside the radical, that's the discriminant only. So b squared minus 4ac doesn't have a radical in it. It's actually the number that's inside the radical. So let's see what that is. Well, we already did that. That b squared minus 4ac, we already evaluated that once inside my radical. That's when we did the 16 squared minus 4 times a times c. And we got the result, and that ended up being 64. Wasn't that 64? And now we'll go ahead and classify the solutions as specifically as possible. So we've got a list here: rational, irrational, non-real. What we want to do is go ahead and classify those solution values. In this case, x equals -2 and x equals -6 as specifically as possible. And so first thing we want to do is, are these real or non-real numbers? They're real. Are they rational or irrational? Well, because they can be expressed as a fraction, they're rational numbers, and so they're real, rational, and there's two of them. And so we're going to go classify them as number and type. So we would say 2 real, comma, rational solutions. Keep in mind if there were radicals in them that didn't reduce, like a 2 plus or minus root 6, that would be 2 real irrational solutions. If there were i's in your answer, as you saw in your homework assignment last night, right? For example, if you got 4 plus or minus 3i, right? That would be 2 non-real solutions, and so on and so forth. And so we're going to classify them by number and type. Even though your directions just talk about the type, I want you to state how many there are as well. Does that make sense? Awesome. All right, so now we're going to go ahead and scooch into our cooperative learning groups. I'm going to go ahead and pause the recording, and then we're going to come back together for our summary. So we'll use our summary for today's closure. Based on a quadratic equation, y equals ax squared plus bx plus c in standard form, we can tell all kinds of things about the number and type of solutions and the graph, right, by looking at the equation. So let's go ahead and pin down things like the y-intercept. So if I have a general standard form of a quadratic equation, y equals ax squared plus bx plus c, we can determine the y-intercept simply by looking at the equation. We know it'll always be the 0, c value, my constant in my standard form quadratic equation. So 0, c is the y-intercept of my graph. How do you determine the axis of symmetry? Well, the axis of symmetry is the x value, right, from the first portion of my quadratic formula. X equals opposite of b over 2a, and that is the equation of the axis of symmetry. So x equals opposite of b over twice the value of a. I can plug in the values for a and b into that, and that'll tell me the equation of the axis of symmetry. Finding the vertex then is going one step further. I first get my x coordinate of the vertex, which is the same as the axis of symmetry, x equals opposite of b over 2a, and then plug that x equals opposite of b over 2a into my original function rule, y equals, and solve for y. Then I'll write my vertex as a point x comma y. So how can we say that? Well, we'll say plug x equals opposite of b over 2a into my y equals equation and evaluate. Semicolon, and then write my vertex as a point. X comma y. So we'll take x equals opposite of b over 2a, that's my x coordinate of the vertex, plug that into my y equals equation function rule and evaluate, and then write my final vertex as a point, x comma y. Specifically explain how A affects the graph. Well, A tells us several things, right? If A is positive, we know we have a right side up parabola. So if A is positive, then we have a right side up parabola. Versus A negative, then we saw, and we did that in our in that second one, we saw an upside down, or in our Bellwork, we saw an upside down parabola. So if A is negative, we have an upside down parabola, opposite orientation of our parent function. If A is larger than 1, right? If A is larger than 1, we're going to have a steeper graph than my parent function. So we can go ahead and specify that as well. A greater than 1, and I'll go ahead and say absolute value just because it could be positive or negative. So if absolute value of A is greater than 1, then what does that do? That makes a taller, steeper graph. Versus absolute value of A between 0 and 1, that's a fraction like 1/2. You saw that with your 1/2, you were less steep. You had shorter y coordinates in relation to the parent function. So I'm going to say if absolute value of A is in between 0 and 1, so that would be values like negative 2/3, right? Positive 1/7. Those would result in a shorter, less steep parabola arm. Awesome. Now let's shift our discussion to that special quantity inside the radical, that discriminant, b squared minus 4ac. And so, in the first one, that first equation we did, our discriminant was 64, right? It was 64. In our second one, and the number of real solutions then, our number of real solutions, we had 2 real solutions. And they were real rational. That's one we did together, right? So 2 real rational when our discriminant was 64. So we'll go ahead and say 2. And they were real, comma, rational. Letter B, go ahead and check and see your discriminant for letter B. What's your discriminant for letter B? Everybody check. Number 7. So what did you guys get for your discriminant for letter B? Ian? 40, right? 40. In that case, there were still 2 solutions. There were 2 solutions. But in this case, they were real irrational. So in this case, they were real irrational. That radical term didn't reduce all the way. It contained a non-perfect square, and that's an indication that we're going to have irrational solutions. So they're still real, but irrational. Be ready to tell the class the discriminant value in C. So everybody find your discriminant value in C. In letter C, what was your discriminant value? Taylor? 0. 0, right? 0, thank you. So when my discriminant was 0, the entire second half of the quadratic formula, it dropped right out. And you were left with that single solution, that single real rational solution. So this is a special case where there is just one solution, and it was real and rational. So one real rational solution. And now for the big excitement, letter D. What did you get for the value of your discriminant in letter D? Everybody find it. So what was your letter D discriminant? No. -8, absolutely. And when we had -8 as our discriminant, when we simplified our square root, our radical, all the way, we ended up getting I in our final answer. And so we ended up getting I in our final answer, an indication that we had non-real solutions. And so our number of real solutions was 0 real solutions. There were 0 real solutions. However, there were still 2 solutions, it's just they were non-real. So the type of solutions were 2 non-real solutions. And we can tell that because of our negative discriminant and because of the I in our final simplified x values. All right, so what is the discriminant? The discriminant was that quantity b squared minus 4ac. And my discriminant is the number I get when I evaluate b squared minus 4ac. It's the quantity inside the radical. There's no radical in your discriminant. It's the number inside the radical. The discriminant can be used to identify the nature of the solutions to the quadratic equation, summarize each case. Here we go. Take a look. Discriminant was positive. We had 2 real solutions. So we had 2 real solutions when the discriminant is positive. They could be rational or irrational, depending upon if the discriminant was a perfect square. If my discriminant was negative, there were no real solutions, but there were 2 non-real solutions. So there was 0 real solutions and 2 non-real solutions if the discriminant was negative. There's still 2 solutions, it's just there are 2 non-real solutions. And lastly, if the discriminant was equal to 0, that was a special case when there was 1 real rational solution. So 1 real rational solution. Great work today, you guys. What questions do you have about our summary? I'm going to go ahead and save the recording then. I'm going to save the recording.